In section 7.3, we're going to begin by looking at what's called a bunch of translation theorems. And this is theorem 7.31 in the textbook. But let's suppose that we have a function f of t that's of exponential order such that its Laplace transform exists. The common notation we've been using is that L of f of t is equal to capital F of s. Let's see what would happen if we tried to compute the Laplace transform of e to the at times f of t. Okay. So this is our function. This is going to go inside of our Laplace transform. We know that this is equal to the integral from 0 to infinity. It's e to the negative st, and then whatever function it is we're trying to transform. This time we're trying to transform e to the at times f of t, which is still just some function of t. The a is obviously a constant, dt. We can rewrite the portion on the inside. This is equal to the integral from 0 to infinity of, combine the exponential terms. We're multiplying by like bases, so we can add the exponents like this, times f of t dt. And then the next thing I'm going to do, let's go ahead and factor out the common terms from that e. I can factor a negative sign out because we want the first term to be positive. We can also factor a t out, and I'll put that at the back end. And then this would become an s minus a. And then f of t dt. And we want to explain what exactly is this equal to. Okay, let's come back for a moment ago. So again, in the definition of L of f of t, the thing that we're calling f of s, which is capital F of s, again, it was by definition, this was the integral from 0 to infinity of e to the negative st f of t dt. And remember, f, capital F, that is a function of s, where what s is it's kind of like the coefficient that's between the negative sign and the t. Okay, so that's what our capital F is a function of. If we look by analogy, what is between the negative sign and the t and the exponent here? Well, it's s minus a. So this is actually the Laplace transform of f, but at s minus a. And so essentially what happens here is that if we multiply the original function f of t by e to the at, the corresponding result that we get is a translation to its Laplace transform. Most of you probably recall from some kind of algebra class, previously, let's suppose that this is the graph of f of s. So let's suppose that f of s looks like this. If a is greater than 0, then the graph of f of s minus a would simply be translated a units to the right. And then, of course, if this was s plus a, then essentially a would have been negative, and would have been the translation of the Laplace transform, but moved to the left. Okay. So this is a brand new result. This is one of our translation theorems. This is important to know this. So let me just kind of rewrite it one more time. So the Laplace transform of e to the at times f of t is simply going to be equal to capital F of s minus a. Okay. Sometimes we will actually use another notation for this. So a notation you will sometimes use that's kind of common is we'll write the Laplace transform of a of t of f of t is equal to the Laplace transform of f of t. And then we'll say where s gets replaced with s minus a. Because at the end of the day, again, it is kind of related to the original Laplace transform, but it's related via this shift, or this translation, if you will. So to kind of represent how those two are related, how the Laplace transform of e to the at times f of t is related to the Laplace transform of f of t, we use this notation. But again, either way you slice it, this is still giving us the Laplace transform of little f, which we call capital F, and with the translation s minus a. So on occasion you will see us use this notation. It just means this. Let's take a look at an example. Okay. In example number 1, let's see if we can find the Laplace transform of e to the 5t times t cubed. So if we think about it, so this is kind of like what we were talking about a moment ago. So this looks very much like the Laplace transform of e to the at times some function of t, right? Where here a is going to be played by the role of 5, and f of t is the function t cubed. We know that this is going to be equal to capital F of s minus a, where capital F of s is the Laplace transform of t cubed. Okay. So let's kind of begin by going ahead and starting out with that. We know that the Laplace transform of t cubed, and we're going to then just switch s to s minus 5. Well, if we go back and look at the theorem we had previously, to do the Laplace transform of t cubed, what we would want to have is we'd want to have the factorial with it. So if we adjust that, what we're going to get is that it should be 3 factorial divided by s factorial. 3 factorial divided by s to the 4th. There we go. And now all we're going to do is we're going to translate this. S is going to go to s minus 5. And so what we get is 3 factorial divided by s minus 5 to the 4th power. And then it's not too hard. We can work that out. 3 factorial is simply 6. So it's 6 divided by s minus 5 raised to the 4th power. Let's do another one. In part B, let's see if we can find the Laplace transform of e to the negative 2t cosine of 4t. Again, here, a, the coefficient of the e to the power here, the coefficient of the exponent t is negative 2. And remember, it's always s going to s minus a. So it's going to be s minus a minus 2, which is going to be s plus 2. So this is going to be equal to the Laplace transform of the cosine of 4t, where we translate s is going to get moved to s plus 2. We look it up, we know that the Laplace transform of the cosine of 4t is going to be s divided by s squared plus 4 squared. This is going to be, everywhere we see an s, we're going to replace it with s plus 2. So we have an s plus 2 in the numerator, divided by, this now becomes s plus 2 squared, and then plus 16. And we can leave it perfectly like that. That looks good. This is our Laplace transform of e to the negative 2t, the cosine of 4t. We can also begin now to talk about the inverse of this theorem. So let's suppose we wanted to find the inverse Laplace transform of a translated Laplace transform. So let's suppose we have the Laplace transform f of s minus a, and we're trying to find its inverse. Essentially, it's going to kind of work the same way. We want to think of this as being the inverse Laplace transform of f of s, where s gets translated to s minus a. Excuse me. We know that the Laplace transform of the inverse Laplace of capital F of s, that's equal to f of little f of t. Excuse me. And then the translation part of this, we know that comes from the factor e to the at multiplying f of t. So this is how we translate an inverse Laplace translated function. F of s minus a is going to be equal to e to the at times little f of t.